Hey, welcome back. In this video, I'm just explaining the method of joints. It's one of the methods that we can use for solving truss problems in statics. In this case, with the method of joints, we basically just isolate each joint. So one of the joints would be A, another would be B, C, D, basically all of these pinned connections. We're going to isolate them all and solve them independently from each other, basically like a particle equilibrium problem in 2D, where we'll just sum up the forces in the x direction and sum up the forces in the y direction, and we know all of the forces are going to be in line with the members themselves. And so knowing that, it actually makes solving this problem pretty easy. So the first thing that we need to do is we actually need to treat our entire truss as just a single structure, and we want to draw the free body diagram for the whole truss. So it'll look something just like this, where we have our one applied force and then we have our two reactions. There's no horizontal applied forces here, so we don't even have to worry about putting a horizontal force here because there's only one vertical force acting down. So both of these supports are just going to be acting opposite to prevent that sort of translation of the whole thing down through the page. You probably already know, if you're at this point in the course, you know that we can just solve for RA and RG if we know F, because we can just do the sum of forces in the y direction and then the sum of moments about any point. It might be easy to do the sum of moments about point A, but if we do those two equations, then we'll solve for RA and RG. Once we have those, then we can actually proceed with using the method of joints, and what we'll do is we'll draw a free body diagram of all of the individual joints. So what you're looking at here is a free body diagram of each joint. The blue arrows are the external forces that we know. One was the applied force, and the two other ones were the reactions that we're able to solve for when we draw the free body diagram of the whole truss. And all these black arrows are unknown forces. These are the internal forces of the members. So they're directed along the lines that the actual members follow. And what I've done is I've always drawn them in tension, so they're always pointing away from the joints. For example, this AB would be the internal force of inside the member AB, and at A it's in tension pulling away from A, and at B it's in tension pulling away from B, because if a rod is in tension, it will be in tension everywhere. If it's in compression, it will be in compression everywhere. So if we're able to solve for AB here, and if we figure out if it's tension or compression, then we'll instantly know what it is here. And again, the convention is to draw them in tension, so when we're going through and solving this, we'll be solving for the magnitudes of the forces, and if we find a positive magnitude, that means we've correctly assumed that it's in tension, and if we find a negative magnitude, that means we've got the magnitude correct, but we've just have the sense wrong, so we're actually, if we have a negative value, it should be in compression. So one other really important thing to know about this type of problem is if we go back up here and look at the original truss, if all of the members are the same length, that means that each angle in here will be equal to each other and they'll all be 60 degrees. So watch out for that in problems, because that's usually what's happening. If they're not the same length, then it'll usually be specified, but otherwise we're always having 60-degree angles in these problems, which makes our life pretty easy. Okay, so when we want to start solving these, in 2 dimensions, we can solve for a maximum of 2 unknowns at any point in time. So for example, if we wanted to look at solving the particle equilibrium here at joint G, we would just take the sum of forces in the x direction and the sum of forces in the y direction, and that would be enough to solve for these 2 members here, these 2 unknowns. If it turns out that we find out that one of these is, let's say, in compression, so we go through and we get a negative value for Fg here, then what we would do is we would kind of correct ourselves. Where do we go? There we go. We would correct ourselves. Once we know it, we would draw it here as compression. Let's pretend this one was still in tension or whatever, but then this guy, if Fg is in compression anywhere, it has to be in compression everywhere else. So this guy would be in compression. So then when we move on to solve for the particle equilibrium here at joint F, we would draw this in compression because we know that's the actual direction, but we would still leave the 2 unknowns in tension. So then when we go again here solving this, when we look at it, we have one known and then 2 unknowns. We have enough using sum of force in x and y, and knowing the angles, which all happen to be 60 degrees, that we can solve for these other 2 unknowns. And then once we do that, if we find some of them to be in compression, we repeat the process, and then we continue on the whole way across the truss, and then eventually we'll be able to solve for all of the forces in all of the members. We also could have started on this end and worked this way, but I think you get the point now. So That's the method of joints kind of in a nutshell. In the next video, if you join me there, we'll actually work through using the method of joints with actual numbers, and hopefully it'll make more sense. Okay, see you there.